Good morning, or afternoon, whenever you're actually looking at this. Today we're going to move on in our notes to the formation of the universe. So go ahead and get your notes out. Should be in universe and all those stars. Clickety click. You should already have stuff highlighted. So we're going to go down to page 2. And the formation of the universe, the theory is called the Big Bang Theory. And I'm not talking about like the show or anything. But if we're looking at this, the universe formed 13.8 billion years ago from one large explosion and a sudden release of very large amounts of energy. And that might seem far-fetched, but we're going to go over the evidences that scientists have looked at, and it does kind of make sense. So just be aware of that. So if you're like, hold up, there's no way, buckle up. Okay, so as the universe cooled and expanded, some of the energy changed to matter and mass, and finally stars and galaxies. And what you see in the back here is this equation that you guys have seen many times before, E equals mc squared. So energy equals mass times the speed of light squared. And all this is showing you is that E, or energy, can turn into mass. That's all that's showing. So if you're like, wait a minute, how can energy change into matter or mass? That right there is how. Okay, so if we're looking at your notes, you should probably highlight universe formed 13.8 billion years ago. All right, from one large explosion, a sudden release of large amounts of energy. As the universe cooled and expanded, some of the energy changed to matter or mass. So as the universe cooled and expanded, let's highlight that. Some of the energy changed to matter. Let's highlight that. All right, so here are the evidences that back that up, or that scientists observed and therefore came to this conclusion. The first evidence is like the most obvious and easiest, I think. So evidence of the Big Bang Theory. So the universe is currently expanding outward. So it's out here, which means if it's expanding right now, that means if you would reverse that and go back into the past, what's getting bigger now would actually be getting smaller. Like if you could rewind, all right, what we're seeing going out now in the past was closer together. All right, so that makes sense, right? So on your notes, you need to draw on here, and the easiest way to do it is to grab that Control-C, Control-V, and you just make it bigger. Boop. Control-C, Control-V, and make it bigger and bigger. Uh-oh. Come on now. There we go. Bigger and bigger. Doop, 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 doop. And you can see there's lots of clouds. There's stars kind of drawn in there. So that is what I would do. I would show that it started in a small spot and over time it's gotten bigger and bigger. So we see it expanding now. So in our brains, we're like, oh, it used to be closer together. Okay. The next evidence of the Big Bang Theory. So cosmic background radiation. So this is kind of harder to understand. So it's energy left over from the Big Bang. When we look out into space, and actually a little bit of background, there were some guys, Anzio and Pennis, something like that, who they were studying space, and so they found this big radio telescope, and they were like, oh, so like it detects radio waves. They were like, let's just point it out into space, see what we pick up. And so they pointed it out to a place in space that didn't have any stars. And they're like, cool, let's see, like that's going to be our control. That's the thing that we'll compare everything else to. So they point it out into space and they get this weird like feedback, and they're like, what the crap is that? And so they try again and again, and they kept picking up wavelengths, all right, specifically microwaves. And so then they started pointing it in other places where it should be clear. They pointed at stars, they pointed at the moon, they pointed it at all different stuff in space. And no matter where they pointed it, they kept getting these microwaves. So when we look out into space, we see energy spread out everywhere. It's a longer wavelength, microwaves, because it's spread out over time as the universe expanded and cooled. So when the Big Bang happened, it was a lot of energy, a lot of like really tight waves because it's hot, there's more energy. But as it spread out, the wavelengths got spread out too and cooled down, and now we're at microwaves everywhere out in space. So in your notes, draw the wavelength to demonstrate the energy from the beginning of the Big Bang until now. So if I click on this and I get my scribble tool and I want it, I don't know if I can see it. I might have to make it white. So scribble, scribble, scribble. I'm drawing really intense close waves, and then as time goes by, I'm going to make these waves bigger and longer. Okay, and I want that to be white since it's on that background. Save and close. So high energy initially. As things spread out and get bigger and bigger, the wavelengths get bigger too. Okay. The last piece of evidence is probably the most confusing. See, that's what I tried to draw. It's the WMAP satellite image. So it's over here, and it's a picture of the matter distributed in the universe. So we said there's energy, this low energy microwaves, low wavelength everywhere. What we also see is as it cools and expands, you're going to have stuff start clumping together, right? That's just the way gravity works. So as it cools and matter starts forming, you have atoms, you have stars starting to form. Stars have mass, and so it's going to start pulling stuff together. And that makes sense. When we look out into space, we actually look at like the matter in space, not just the energy, the matter, it's clumped up, which means that over time, matter formed and it started attracting things, which makes sense. Okay, so that's what that's showing you right down here. Okay, and that's where we're going to end today.